In this lecture, I'd like to say a few words about the app that you are supposed to develop for Chapter 4, CryptoNote. The app is intended to expose, among other things, some aspects of cryptography, the art of hiding information, so that it cannot be intercepted and interpreted by others. Cryptography has been pursued for thousands of years. It has gained popularity in the Cold War, of course, because, between spies and so on. But then, with the widespread usage of the internet, privacy concerns, and then using the internet to conduct business, it became very important that people be able to communicate securely. The app of this lecture leverages a cipher that is known as the Visionaire cipher that allows you to scramble, if you like, the information so that it's difficult to unscramble it, except if you know the key and if you are the intended recipient of the information. So I'd like to do an example first to get a feel for the cipher that is being used, introduce some terminology, and then write a class that carries out this encryption. So the idea is simple. There is a sender and a receiver. Sender typically is known as Alice, and the receiver is Bob. So Alice wants to send something to Bob. Alice has a plain text, which means it's written in human language. Something like, I would like to buy 10 RBC shares, something like that. The plain text, I'm showing it in green. And she has a key that using it, the plain text will be scrambled, will be encrypted. After applying the key and the algorithm to the plain text, you end up with a cipher text. I'm showing it in mauve. And that is hard to unscramble if you don't know the key. Now, the algorithm that you use to do this scrambling, there are many such algorithms, and in the case of letters, the Visionaire cipher was at one point thought to be a very, very strong cipher. Let's just take a look at how it does this. I'm gonna restrict the plain text to this alphabet, which is the letters A to Z, uppercase, all right? And I'm gonna assume that the key will always be made up of digits between 0 and n. So the key here is like a PIN rather than a password. We're going to describe the algorithm and implement it in Java without relying on these two conditions. So if you later want to change the alphabet to include lowercase, digits, symbols, or some peculiar subset of characters, you can do that. And you don't have to stick to a pin. You can use the same complicated alphabet that you use for the plain text for the key space. But for the sake of demonstrating how the encryption is done, I'm going to use this these two simple assumptions. So we have our plain text, and we need a key. And I'm going to pick a key made up of 3 digits. Let's say 613. Obviously, the more digits you have in the key, the harder it is for somebody who intercepts the code to exhaustively try every possible key. with 3 digits, you have 1,000 possibilities between 000 and 999. But if you have 10 instead of 3, and they are characters rather than digits, then the space expands exponentially more. So, under these assumptions, how do I encrypt the plain text? Visionaire says, imagine creating a pad, another string, and writing it under the plain text. And you do that, you create this pad by simply repeating the key, concatenating the key with itself. Keep doing this concatenation until you fill up all the spaces under the plain text. So 613, 613, 613. It just so happened now that it divided evenly, but it doesn't matter. If the plain text started at B, here it will stop at 1. All right? So just repeat it enough times so that you have the same length as the plain text. After that, now that you have these 2 strings, the algorithm kicks in, and it says, you want to take the first letter of the plain text and the first letter, or the first character, I should say, of the key, and mix them together to form the first character of the ciphertext. How do I mix them? You must find out the position of B in its alphabet and the position of 6 in the key alphabet, the key space, and add these 2 positions together. That's the rule. So I have here the alphabets, which are all the letters from A to Z. So what's the position of the letter B? Well, I can see here that B appears here. Its position is 1. All right? You can see that now that the index of method in the string class is very handy, because if I put this alphabet A, B, C, D, E, F in a string, and then I take this first character B and I say, does this string contain a B somewhere? And it will give me right away its position in its return. So finding this position is easy. Same thing with the 6. I can easily form an alphabet made up of all the possible digits here between 0 and 9, and again use index of to create that. So I have just created another table that covers the key space of the key between 0 and 9 and corresponding position in that table. I realize this table looks redundant. It's so easy to get the digit, but again, I'm trying to avoid relying on the fact that the key space is made up of digits. If one day it was changed to smiley faces or something, then my approach would scale, would go unchanged. So don't think of those as simply the ASCII code or the order. No, this is just a bunch of, on the left column, it's a bunch of characters, arbitrary character decided by Alice before she sends, and those are the position, the corresponding position. And whenever I am given one of the characters of the plain text, I look it up using index of here to find the corresponding position, and whenever I'm given a character of the key, I look it up in this column here. So let's apply these ideas. So B, we know, is associated with position 1. 6 in the key, here it is associated with position 6. I add 6 and 1 together, and that makes 7. Now, to find out the ciphertext character, I go to position 7 in the alphabet of the plain text, which is here. This is 7, and I see the corresponding character. This is not the index of, this is the opposite. you are substringing out or doing a char at position 7 and extracting a character. So that makes this H. I'll do it once more with U and V. U has position 20, index of will return 20. 1 is 1, so I end up with 20 plus 1, 21, and 21 is V. So I write V. Y and 3, Y is 24, and when you add 3, we have a problem. I'm going to fall off the edge here. So in order to avoid the edge effect, we'll use the same idea that Java uses to avoid edges in the int domain. It treats it circularly. It traps it around. So Y is 24, and I want to go 3 more. 25 is the first, 26 is the second, 27 is the last one. So B is where I want to go. T and 6. T is 19 plus 6, 23. That's X. E and 1 is F. N and 3 is 16. Q. R and 6. R is 17 plus 6. 23 is another X. No, R is 17 plus 6. 23 is X. Let me review this one. This is T plus 6. T is 19. 19 plus 6 is 25. So this is Z. B and 1 is C. C and 3. C is 2 and 3 is 5. That makes it F. Alright? So hopefully I did this correctly. And if so, the answer is H VB ZF QX CF. All right. If I didn't do it correctly, do it carefully to get it right. We'll write the code now and we'll see how it works. So that's the idea. Let me say it one more time. You write the plain text on top. You create a pad by repeating the key as many times as is needed to have something as big as the plain text. If it's bigger, if it exceeds, that's okay, but it shouldn't be less. Then, column by column, you extract a character from the plain text and a corresponding character from the key. To know how to add them, you need to find their position. So use index of to find the position of Y in its alphabet, the position of 3 in its alphabet, add the two numbers wrapping modulo 20, 25, and that gives you the position of the ciphertext character. Use the alphabet again, but this time using substring to find the corresponding letter. So with this in mind, let's go now and write some code to do this. I'm going to create a class. I'm going to call it the visionary class. And in that class, we're going to have, let's see, just like any class, you think about what's the state, which indicates what are the attributes that I must hold, and provide a constructor and the needed methods. So clearly, if Alice and Bob agreed on a key, the magic is that key. So I start with private string key. As usual, all attributes must be private unless they're final. Then we don't care, we can make them public. Then there is a constructor. I'm going to call it public The name of the constructor must be the same as the name of the class, and it takes some parameter, which is the initial value, or the value that Alice and Bob agreed upon for the key. You can call it key, don't worry, it won't shadow the attribute over there because we refer to the attribute using this. So this dot key equal key. Now when a client creates an instance of this class and supplies a key, the instance will be customized, initialized, to hold that particular key as state. Now we need a method that returns a string, which is the ciphertext. So public string encrypt, and it takes a string being the plain text message that's being sent. Let's call it message. So message here is like buy RBC shares, and the key here is 613 in the example I gave. The first order of business is to create this red pad, this string. I need to create this string given the key in order to start the algorithm. Obviously, the encrypt method needs to create this, and the decrypt method, because when Bob receives this ciphertext, how does he go back and recover the plain text? He does the opposite. He first creates the red pad and then look up the position of H and subtract 6 from it to reach B, right? So the pad is needed on both sides for encryption and decryption. So to avoid code redundancy, let's just have a method private just for us. Let's call it make the pad. And it returns a string. And all it needs is the length of the message. All right, so integer, let's call it length. And my intention here is to create the pad by invoking this method and sending it the length of the message. So let's see how we can create this. What I need to do is to take the key, which is simply this dot key, I know it, right? And keep adding it to itself. So I need clearly an accumulator. Let's call it result. String result. It starts off being an empty string, and then every time we take its old value result and add to it this dot key. So clearly I need to do this in a loop, but the body of the loop is simply tacking another key at the end of the result that I have formed. Now, once the loop is done, I simply return result. So the question, I suppose, is what kind of loop is appropriate? Well, you ask yourself, you want to repeat this process of concatenating the key, how many times? Do you know? Well, I don't know. It depends on the length of this thing. I need to keep doing it as long as I am less than the length of the message. So I can use a for loop or a while loop. Both of them work just fine, as long as result.length is less than the length that they sent me. Then I need to do more. Once it becomes equal or it exceeds it, I return the result. Notice that the result that will be returned could be longer than the message, which is fine. All I need is to make sure it's not less. If you're very picky, you can here substring it to pick only as many characters as length from it, but there is no need for that. All right. So now that we have the pad, back to here, I have the red line and I have the green line. I need now to go vertically, column by column, to do the encryption. So clearly I need a loop that browses through those columns one by one, from the very first position, which is position 0, to the very last, which is 1 less than the length. So a for loop is very natural here. I can say for integer position 0, and you do this as long as the position is still less than message.length, and every time you move right by incrementing the position. So far so good. Now we are at a particular position. So back in this diagram, I'm somewhere here. I have a particular position. I need to extract the Y from the plain text. This we know how to do. We simply say you take the message and you substring from position pause to position pause +1. Remember, the substring method is peculiar because its first parameter is included and its second parameter is not, it's excluded. So this extracts really just one character from the message, the one residing at position pause. So now I have the Y in my example here. Let's give it a name. Let's call this, it's a message character that I'm looking at. All right, same thing, I'll copy it. I'm gonna get a pad character, which is from the pad, I'm gonna extract one character from this position. So now I got the Y and the 3. I need to add their positions in their corresponding alphabets. So to do that, I need to create an alphabet for the plain text and an alphabet, just like the tables here. So I'll add a constant here, public as usual. If it's final, make it public. So public final string, and this is the plain text alphabet. So I'm gonna call it the plain text alpha bet. As usual, best practice, you use all uppercase for identifiers that are final. So here I'm going to put A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And I'll have another one containing the alphabet of the key, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'll call it not the plain text, but the key alphabet. All right. So these two statements extracted the characters themselves. The next two statements will find their position in their corresponding alphabets. So I'm going to say, take the plain text alphabet and search in it for the message chart that we looked. And that gives you the position where it finds it. So integer, the message position, and similarly you find by going to the key alphabet, you do the pad position. All right, I got the two positions now. So in this diagram for the Y, I looked it up and I found it 24, and for the 3 I looked it up here and I found it 3. I simply need to add 24 plus 3 circularly, hopefully to reach 1, the position of B. So my job is as simple as the new position for the ciphertext would be, I need to declare it, would be simply the sum of the other two, message position plus the pad position. Now this addition will fall off the edge if you go beyond that, so you need to restrict it to the length of the alphabet, of the plain text alphabet. You can do that in one of two ways. You can add an if statement that says if this exceeds the length, then subtract the length from it. Or you can say simply do this percentage plain text alphabet dot length. Because remember, the remainder operator percentage will work properly in this case. So now in terms of here, I'm imagining I am in position 2 here. So for Y, I got its 24, and for the 3, I got its position 3. 24 plus 3, 27. 27, what's its remainder after dividing it by 25? And the answer would be 2. All right, so now I got the 2, remainder 26, not 25, because the length of this is 26. So 27, remainder 26 is 1. All right, so we got the 1. Now I need a final thing to look up position 1 to see its corresponding character. So if this is the position, then I'm going to say now string the new char is, you take the plain text alphabet and you extract from it the character at no pos. All right, and now that you have that character, add it to your ciphertext. We did not have a result here. Let's have a string result, currently empty, and every time around we simply add to it this no char that we got. No char. When this is done, we return the result. So let's review our code one more time. We want to encrypt a message, MSG. We said the ciphertext initially, the result is empty. We created our pad, and then we went through the characters of the plain text one by one from left to right. For every position, we found the character of the message at that position, the character of the pad at that position, and we changed them from strings to integer by looking up their position. So for the message character, we looked it up in the plain text alphabet. For the, this is wrong, this is the pad, not message. For the pad character, we looked it up in the key alphabet. That gave us the two positions. and from these two positions we added them using the percentage operator to wrap it around, and that gave us the position finally of the resulting character. We looked it up in the plaintext alphabet to find its corresponding character and concatenated it with the result and returned the result. As a quick check, let's add a client Visionaire v equal new Visionaire and give it the key that we did earlier, and simply let's try to encrypt v.encrypt. What was the plain text over there? By 10 RBC, so by 10 RBC, and let's see what's the result of the encryption. If I run the main method, run vigmain, and it says HVB ZFQ XCF. Yeah, it looks like we did it correctly. All right. In terms of decryption, right, the story is very similar. Encryption and decryption work the same way. You still need a pad, right, to do that. You still need to go through the characters left to right one by one. You extract the two characters, you look up their two position. The only difference is instead of adding them, you want to subtract them. All right, so really the decrypt method could be copied, just copy and paste from the encrypt, except you replace the plus with a minus, with a little caveat. The percentage operator in Java is not exactly the mod operator. Mod, as you know from math, forces everything to be in the range 0 to the modulus minus 1. The percentage operator works like that for positive values, but it doesn't work like that for negative values. So if you got a message position equal 5 and you subtract from it, let's say 6, 5 minus 6 is minus 1. If you do a percentage in the alphabet, it remains minus 1. It doesn't push it up. So as a suggestion, when you write the decrypt method, perhaps you want to do the if statement in this case instead of the percentage. So let me do it here even for the encryption, just to give you an idea of what needs to be done. So you can say if the new position happen to be greater than the length, then go ahead and reduce it by the length. Else, if the new position is less than 0, then go ahead and increase it by that. So these, let me separate them off the code so you can see it. This if else if will take care of the proper mathematical mod operation. So perhaps what you want to do is to put this in a private method to avoid code redundancy. Put it in a private method and call it something like circular shifting or stay inside or something. And then the encrypt and the decrypt method will differ only by this sign. All right? You can even fuse them into one method that takes another Boolean that knows whether that tells it whether it should encrypt or decrypt and change the sign one way or the other. So that was an overview of what needs to be done for the app CryptoNote that allows you to create notes on your phone and then encrypt them using a key, and perhaps send them by email or do anything with them if the recipient has the key. Using the class that we created in the app, they can easily decrypt it. All right, that's the end of this lecture.